By the time students reach middle school, educators are seeing a distinct drop in spatial reasoning and a rise in math anxiety. This is the cognitive cost of moving from early physical counting into screen-based abstraction. The primary obstacle to long-term mathematical proficiency is how we introduce physical tools in the first place. The educational approach is entirely fragmented. A student learns to count using unifix cubes, switches to base 10 blocks for place value, and uses separate area models for multiplication. Eventually, they outgrow and abandon these tools. Because these disjointed blocks don't carry over from year to year, the student fails to develop a coherent mental schema. Numerical logic becomes a series of isolated, memorized rules, rather than an organic extension of geometry. To build a coherent mental schema, a learner requires cognitive continuity. Rather than adding more specialized manipulatives, the Pythabacus adopts a unified tool approach, a single device that evolves alongside the learner from kindergarten to 8th grade. The physical architecture of any manipulative dictates the cognitive limits of the student using it. A tool built only for linear counting traps the student's understanding of numbers in one dimension. This graphic shows the diamond orientation of the Pythagorean multiplication table. By mapping numbers across a two-dimensional grid from 1 to 100, it forces the learner to move past linear arithmetic and see factors as spatial relationships. This theoretical table translates into the wooden framework of the Pythabacus. Natural beads across horizontal rods mirror the upper half of the multiplication diamond. The bottom row of gold beads acts as a structural anchor, revealing the intrinsic symmetry. With this orientation, products transform into physical areas. Students visualize factors as the actual dimensions of a physical rectangle, rather than floating abstract digits. By cementing numerical logic inside disfixed geometry, the student's physical interaction remains consistent and supportive, even as the algebraic equations become complex. In the 3rd and 4th grades, the tool shifts students away from the rote calculation support of early elementary years, focusing instead on internalizing advanced number theory. This arrangement models a simple arithmetic statement, 3 times 2. By displacing the gold bottom factors, the student reveals the product as a solid, physical, rectangular array of green beads. When the sum of the factors is greater than 10, like 6 times 8, the student loops the count of the second factor. The remaining red beads against the left post equal the tens, and the displaced green array equals the ones. This physical counting naturally leads to the verification of mathematical properties, such as the commutative property. If a student needs to prove that 3 times 4 equals 4 times 3, they rotate this exact configuration of beads, demonstrating that the physical mass remains equivalent regardless of its orientation on the board. Arithmetic becomes the physical construction of spatial properties, replacing the need for rote memorization. Moving into the 5th and 6th grades, the Pythabacus bridges between basic whole numbers and proportional reasoning. This initial setup shows the beginning of partial product modeling. Students construct area models for multi-digit multiplication, such as 23 times 4, by partitioning the representative bead groups. By breaking the problem down, the 23 is geometrically split. The student physically displaces the 2, 3, and 4 bead sections across the horizontal rods. The revealed rectangle is now partitioned. The upper part of the array represents the tens, calculating 2 times 4 to equal 8. The lower part represents the ones, calculating 3 times 4 to equal 12. This final map of geometric clusters explicitly models the distributive property in action. By giving the distributive property physical mass and dimension, students comprehend the underlying mechanics of algorithms. They are building the math rather than blindly executing steps on paper. Next, the tool is used to tackle abstract relationships, like finding the greatest common factor between two distinct numbers. Here we are comparing the products 12 and 8. The student builds the 12 as a regular rectangle positioned above a triangular grouping, using a gold base factor equal to 3. The student counts out beads from the 12 to make a regular rectangle equaling the 8. The 8 overlaps the 12 right along the longest side, physically revealing a greatest common factor of 4. By turning the search for a common factor into a physical exception hunt for overlapping edges, divisibility is experienced as a spatial property rather than an abstract rule. As the curriculum advances into middle school geometry, those basic gold bead arrays are recontextualized to model fraction multiplication. serving as physical boundaries for rational numbers. Students connect perfect squares to their numerical root, tracking them along the vertical and diagonal boundaries. Shifting a rod demonstrates squares emerging as the sum of consecutive odd numbers, 1, 4, 9, and 16. This sets the stage for the tool's eponymous function, physically constructing and proving the Pythagorean theorem. A right triangle is constructed directly on the board. Legs A and B are mapped as the factors along the sides of the A squared and B squared regions, anchored in the lower right and upper right corners. The hypotenuse C is derived directly from the central diagonal region. The student counts the smaller triangles inside the C squared area and sees it exactly matches the combined areas of the A and B squared configurations. The mechanics used for third-grade arrays transition directly into advanced geometric proofs on the exact same coordinate system. Mathematical understanding requires continuous building. When we replace disjointed, throwaway blocks with a single, interconnected architecture, a student's spatial reasoning compounds year over year. It's educators with vertical alignment, a single investment that maintains a consistent mathematical language from kindergarten through 8th grade. The system directly satisfies mathematical standards. It requires students to engage in rigorous geometric modeling and to construct viable physical arguments to defend their answers. This physical grounding is critical. Schools are currently facing a digital backlash, struggling to assess actual learning amid a flood of AI-generated homework answers. The Pythabacus functions as a tangible anti-cheat mechanism. A student cannot fake their way through it. They must manually manipulate the board to prove exactly why an operation works. It eliminates the illusion of knowledge. By requiring tactile proof for every mathematical abstraction, it ensures the transition from performative calculation to comprehension